Hello, everyone. Welcome back to episode 81 of the Stanford MLSys seminar series. My name is Dan Fu. Today, I'm joined by Ben Spector. So Ben is filling in for Simran this week, but in the winter quarter, starting the next calendar year, he'll be one of a little crew of folks who will be taking over. Great to get to know him. This is like his internship week. If you don't like him, feel free to leave comments down below, and we'll ignore them, but we'll take the feedback.
I'll take the feedback. It's okay. I can take it.
All right. Ben, do you want to introduce yourself quickly?
Yeah, sure. I'm a second-year PhD student here at Stanford. I work at the intersection of AI and systems. So previously, I worked on speculative decoding and sort of helping make that run faster. These days, I'm more interested in training and how you kind of build hardware-aware training algorithms and that sort of thing. So yeah, it's great to be here.
Cool. And today we are joined by Martin Maas. So Martin is a staff research scientist at Google DeepMind. He's interested in language runtimes, computer architecture, systems, machine learning, with a focus on kind of doing the ML for sys side of the problems, machine learning for systems. Before Google, he was doing a PhD at Berkeley. And today he's going to be talking about a taxonomy of machine learning for systems problems. So we're very excited to hear from him. I'm very excited to kind of hear about this side of the side of things, which of course will play a theme throughout the rest of the quarter. Martin, would you like to go ahead and take it away?
Thank you so much for the introduction, and thanks for having me. So today I want to talk about machine learning for systems. And as you all know, machine learning has been applied in a wide range of different systems areas. People have been using it for things like data center scheduling. People have used it in compilers and runtime systems. And people have even applied it in areas like hardware design. And what do we mean actually by applying machine learning to a system? And here's an attempt at a definition. So systems have all kinds of policies that you can call a system policy. So given the hardware software components, these systems make decisions about how to execute computer programs. And a system policy is basically anything that describes how these decisions are made. So for example, a compiler pass is a system policy. A branch predictor is a system policy. Or a hardware component that decides how a program is run would also be a system policy. And so starting from the definition, we can now define machine learning for systems as anything that applies machine learning in the implementation of such a system policy. And there has been a lot of work in recent years about using this kind of approach. For example, there has been ML for databases, there has been ML used in compilers, in networking, various different components of hardware, etc. And there are a couple of common patterns that are emerging. And a common way of applying machine learning in a new context is to basically take an existing system, take a particular policy, and replace it with machine learning. However, whenever this approach is applied, it leads to a number of open and questions that are related to applying ML in this context. So for example, we just applied ML, we got a better result. But what is it that actually makes machine learning better than the baseline? Sometimes that is not fully understood, for example. Second, what is it actually that the model is learning? Is the model generalizing something that it didn't know previously, or is it maybe overfitting to a prior distribution and that allows it to make better decisions? That's also a question that's oftentimes not known. Somewhat related, there are many different ways machine learning could be applied to any given system problem. So how do we know what the best learning approach is for a given problem? And finally, once we have applied machine learning and we have seen a gain, could this gain have been achieved more cheaply, either using a conventional technique or using a cheaper machine learning approach? And these questions are kind of universal, and they span all the various different areas in which machine learning is applied in a systems context. And what I want to convince you in this talk is that in order to answer these questions, we need a shared terminology to discuss them, and also a shared methodology of how to approach these questions and find answers to them, and basically figure out what is it actually that machine learning allows us to do, and how is it applied well in the systems context. And so in this talk today, I want to start by an attempt at such a taxonomy and methodology. And I'd then like to give you two examples of ML for systems and how they fit in with this taxonomy. Specifically, one that draws a connection between AI for code and systems, in particular memory management is one example. And also on how ML for system applies in the context of allocation for ML accelerators, which is a common problem in ML compilers. Okay, so let's talk about ML for systems and how we might create a taxonomy for this kind of area. And so this came out of a paper that's a couple of years old at this point. And this is basically a first attempt at figuring out what is it that these different ML for systems approaches have in common, and what are the ways in which we can answer these questions I mentioned before. And so the first question to ask is, as we're looking at these system policies and we're applying machine learning to them, what do these system policies actually look like? And I would argue there's really four different kinds of system policies. The first one, which is probably the most common one, is what I call an ad hoc policy. So this is when you build a system and you are just putting some decision logic in there to make the decision that you need to make. And oftentimes that just works well enough and you leave it there. So I would argue most decisions in systems are really made by ad hoc policies. So for example, if you consider a compiler and you have a policy that decides whether to inline functions or not, an ad hoc policy could just say inline this function if it has less than 10 instructions. And that's simple. It probably works quite well. And then you don't need to make any decisions beyond that. The next type of policy is what I call an empirically tuned policy. So these are policies that may be more complex and are trying to solve a problem in a better way. And they're oftentimes developed by using benchmarks and basically developing algorithms and techniques to make these benchmarks better. So in the context of inlining policies and compilers, this might be an algorithm that looks at the call graph of a program, applies some complex algorithm, maybe some rules to determine should I inline or shouldn't I inline. The next type of policy is what I call a data-driven policy. And the difference to the previous one in this case is that we don't have to write one policy that does the same thing for every workload, but we're actually able to measure workloads and have these measurements feed into the decision that the policy makes. The classic example in compilers is feedback-directed optimization, in this case, feedback-directed inlining, where you run the application, you measure the application, how it is running, and that can then inform the inlining decisions in the compiler. And then the fourth type of policy is an adaptive data-driven policy. And in this case, you do the same thing, but you can actually revisit your decisions at runtime. So for example, if you have a just-in-time compiler that is running within a system, it can continuously measure the application, revisit any decisions that it made, and then revise inlining decisions over time. And so why do these different types of policies matter? I would argue that what machine learning typically allows us to do is to go from an empirically tuned to a data-driven policy. So in many cases where you might develop a traditional algorithm, it is machine learning that then allows you to make that algorithm based on feedback that was gathered by the model. And so once we consider this as the starting point, we can now start looking at the entire policy end to end and ask ourselves, okay, if machine learning is what gets us from empirically tuned to data-driven, what is it actually exactly that the machine learning model is learning? And this allows us to then extract the exact portion of the problem that requires learning. And doing that has a number of advantages because it now allows drawing connections between different machine learning persistence problems. It allows developing best practices and benchmarks and data sets because it doesn't become a one-off question anymore. It becomes a question that spans basically various different areas. So what are the ways in which machine learning enables data-driven policies and in which they are used across different system problems? So here's an attempt at a taxonomy that doesn't cover all of the different ways in which people have used machine learning, but I would argue it covers a fairly large range of them. So a very common approach of using machine learning is for anomaly detection. So for example, detecting whether a program is experiencing performance regressions. And this is true across a wide range of areas, and there are some established techniques like autoencoders or clustering techniques to solve this kind of problem. The next type of shared pattern between these different ML for systems problems is forecasting. So trying to predict what is the future application behavior. So for example, what are the future resource demands of an application? And this is also a well-established field. People of time series modeling with neural networks, decision trees can be used in this area, etc. It's a common application of supervised learning. Then a third category is extrapolation. So in this case, you have a couple of examples from, for example, programs or inputs or something within the system that you've seen before, and you're trying to apply what you've learned to a new pattern. So for example, if you have a scheduler and you have programs that are either scale up or scale out, you might want to predict for a new incoming program, is it one or the other? And that's again an application of supervised learning. There's been lots of work on using neural networks for this, for decision trees and so on. Fourth category is discovery. And so this one is slightly different from the three before, in that here machine learning is not really used to make decisions at runtime, but it is used to come up with new policies that can then be deployed in the system. So for example, you might use machine learning to determine a new caching policy and then build that policy into your system. And so common approaches here are reinforcement learning to search a space, or imitation learning, where you start with an expensive technique and you train a model against the output from that technique. And finally, the fifth category is optimization. There are a wide range of different optimization problems and systems, including in areas like ML for hardware design, auto tuners, and so on, and various different ways in which machine learning can help solve these optimization problems. Now, there are ways in which machine learning is applied to systems that don't apply into any of these categories, but they cover a fair set of the space. And now I want to go through two examples that fit into this category and talk a little bit about how these shared patterns apply across a wider range and are kind of repeatable from one area to the other. And so the first area I want to talk about is AI for code and how it connects to ML for systems. And the way I want to do this is by talking about one specific systems problem, namely memory management. Now, AI for code has seen quite a bit of attention lately. People have used all kinds of different machine learning models to reason about code. But how does that connect into systems? And I would argue one area where it can help in particular is lower levels of the system stack that can benefit from knowing about what the code is doing. And one good example of this is memory allocators. So what does a memory allocator do? Let's say you have a C++ application. It allocates objects by calling new. It deletes them by calling delete. Whenever you have one of these calls, it goes into the memory allocator, for example, tcmalloc. There are other ones as well. And what the memory allocator then needs to do is it needs to decide where in memory should it place the object. One way to visualize this is in a graph like this, where the x-axis is time and the y-axis is the location in memory. And then every object can be represented as a rectangle. So the height of the rectangle is the size of the object. The width of the rectangle is the lifetime, so the time between the call to new and when the object got deleted. And then basically a memory allocator needs to decide where in memory is it going to place it. So what is the y coordinate of this object going to be? Now, in the context of C++ in particular, there is a constraint, because once you have placed the object, you can't move it anymore. And from a memory management perspective, it matters especially which objects are placed together on a shared page. So these systems are typically paged. They use 4 kilobyte or 2 megabyte pages. And you can only return a page back to the operating system and reuse it if the entire page becomes empty. So the goal of the memory allocator is, among other things, to place objects in such a way that a page becomes empty altogether so that you can return it back to the operating system. Now, how does that correspond to code? The challenge is that in order to know how long these objects live and where they need to be placed, the allocator fundamentally needs to interact with code, because that's where the memory allocations actually come from. And so at a high level, the goal of the memory allocator is basically, if I give you a piece of code, how would I manage the code's memory as efficiently as possible? But the memory allocator is limited because it doesn't actually have any understanding of the intention behind what the code does. All it sees is this sequence of requests that are coming in, but it doesn't really know how that connects to the high-level user intent. And I want to argue that AI for code is the way to overcome these limitations by enabling memory allocators to actually reason about the code's intention. Of course, this applies beyond memory allocators. Other low-level systems have the same property, where they interact with the higher levels of the stack and need to reason about user intention. So to give you an example why this matters, let's say you have a program. This is the same visualization from before, and this program is currently using 2 pages, one that has already a number of objects that are very long-lived, so this page will not become free for a while. And then there's a page that has mostly short-lived objects, so it becomes available very quickly. And the memory allocator has to now decide to place 2 objects, one shown in red and one shown in yellow. And if it doesn't know anything about these objects, it basically has to make a random choice. Is it going to put the red one into page 1 and the yellow one into page 2, or the other way around? If it happens to make the decision where it puts the long-lived object on the long-lived page, everything is well, because the second page becomes empty quickly and can be returned to the operating system. But if it makes the choice the other way around, you now basically have long-lived objects on both of these pages, and you can return neither back to the operating system, which means that you're now basically wasting half your memory, essentially. And the problem is that the only way you could have avoided this is to actually understand which of the objects is long-lived and which one is short-lived, which is directly a function of the application code's behavior. And so if you can reason about what the code is going to do, you can make this decision well. But if you don't have any information to go by, it basically becomes a coin flip. And this is actually a problem that occurs in running workloads. So here's a server running as a synthetic trace, and red in this case shows the wasted memory from this kind of fragmentation. So these decisions do actually matter. Okay, so how can we actually leverage ML to reason about the program that is using the memory allocator in order to make the decisions better? And the answer is that when we do an allocation, we can actually see a little bit into the code, because we can see the stack trace that we have at the time we make an allocation. And that stack trace encodes lots of symbols from function names, from type names, and so on. And those encode programmer intent. So for example, in the stack trace, we see that there is a parameter that has the name parse context, and it's possible that context indicates, okay, maybe this is short-lived, because the context oftentimes does not survive the entire duration, but only a temporary function of the program. Okay, so but how do we extract this meaning? And this is where machine learning comes in. So one way to do this is to treat the symbolized stack traces as text and say, can we apply a language model in order to predict the lifetime of an object based on the symbols in the stack trace? We did something very simple here. We used an LSTM, and we focused on a particular version of this problem where we're looking at generalization between different versions of the same application. We also had a paper recently where we looked at this a little bit more holistically and asked, can you actually generalize across programs as well? It's a similar problem, but it's a lot harder. So once we can make these predictions, which programs are long and short-lived, we can start building this into a memory allocator. And this is something that we published in S+ 2020. And the idea here is basically, you start from a program, you measure the lifetimes of these objects together with a stack trace, you train this model, and then you put the model back into the memory allocator in order to make these allocations in a better way. Now, memory allocators need to make predictions at very low latency. So this model is actually too expensive to run at every allocation. And so what we did in order to make this work at runtime is we actually don't run the model every single time we perform an allocation, but instead we have a hashing mechanism where you can get a very cheap hash. You cache most of the allocations, and only if you are not finding a cached result, then you run the model and you turn back to the allocator. And so this is a pattern that applies in general, where if you have an expensive model that's too expensive to run while the application is executing, oftentimes the results can be cached, and then you can basically run the model only when you find an uncached result. Okay, so with the model and this caching mechanism, we have lifetime predictions. How can these predictions now be used to reduce fragmentation and increase the memory usage? So what we did here was we then implemented a new type of memory allocator that's basically asking the question, if you have these predictions of the lifetime of the object, they may sometimes be wrong, but they're directionally correct. How would you redesign a memory allocator on this way? and it led to a somewhat new design that is basically keeping track of predictions and trying to detect when the model was wrong and adapt to these mispredictions. And I think the pattern that we see here is that by making a prediction with a model, we can now rethink this fairly old problem and ask, with this prediction, how would we build this traditional system in a different way? And this is actually something that applies, I think, fairly widely to ML for systems. Because we figured out how to use machine learning, we use it for this specific thing of predicting this property. We can now redesign the system around this one prediction, and everything except for that model that makes this prediction is traditional logic. Only the lifetime prediction in this case is machine learning. And this applies in areas too. For example, we had a paper also where we showed that the same approach applies to storage systems, where you have a model to predict just one property, and then you basically build the system around this property prediction. And so this is an instance of this extrapolation pattern, where you use machine learning just to predict one property, and then you build the rest of the system around it in a traditional way. And it is a pattern that's repeatable across a fairly wide range of systems problems. So the second example I want to talk about is quite different, and it touches a little bit on the systems for ML aspect as well. So this is about allocation in ML accelerators. And so ML accelerators exist in a range of different places. So for example, at Google, we have a data center TPUs. We have machine accelerator in the Google Pixel phone. There's also embedded edge TPUs. And in the ML compiler space, there are a number of problems related to how to map a execution graph down to the memory buffers on these accelerators. And that is generally a hard problem. There are several pieces to it. One is what's called memory assignment. So you have the data flow graph, you have different buffers. You need to determine which memory in the memory hierarchy should each buffer be allocated to. And then there's a second problem called memory allocation, which is that once you have assigned the buffers to a particular memory, so for example, on-chip memory, how do you decide within this memory where this buffer should be placed? And that's the problem we're specifically focusing on in this work. Now, this actually looks very similar to the C++ memory allocation problem that I showed you earlier. And in fact, it can be visualized in the same way. Once again, the x-axis is time, the y-axis is the location in memory. But the main difference is that in the machine learning case, we actually know the start and end time statically. We don't need to predict it. We already know exactly the time when the buffer will be created, and we know the time when the buffer will go away. So the resulting problem now looks like this. Given a sequence of fixed buffers where we know the start and end time, we need to place them in memory such that the total used memory never exceeds the capacity of the memory that we assigned it to. So for example, on-chip memory in this case. And it turns out that this is actually a complex NP-hard problem. So here's a real-world model and what this packing problem looks like. Basically, you have all these rectangles and you try to place them in a way that it doesn't exceed a particular limit. And there's traditionally two approaches of doing this. One is you can use heuristics, which are fast, but they don't always find a solution. So if the heuristic can find a solution, that's usually the preferred approach because it's very fast, but it might just not be able to solve the problem because it's NP-hard. The alternative is to use a solver, such as, for example, an ILP solver. And these solvers can handle complex inputs, but they can sometimes run for a very, very long time to find that input. And that can be a problem for ML compilers, particularly if they are in the critical path. And so what we did in this work is we developed a new kind of allocator called telemalloc. And the goal here was to combine heuristics and solvers in order to get the best of both worlds. Basically something that has the power of a solver to find solutions that the heuristic can't find, but also being faster. And this was published at S+ earlier this year. Now, this approach doesn't use any machine learning yet, but what it does is it combines heuristics and CP solvers in a way where they run in a loop. So the heuristic makes one decision, so it places one buffer. It communicates the decision to the CP solver, constraint programming solver, which will then upgrade all of its constraints, decide whether the problem just became unsolvable. If it became unsolvable, it communicates back to the heuristic that it should stop and try something else. And it can also communicate back to the heuristic any of the updated constraints that it has learned. So the heuristic now has more information to work with because it gets the input from the CP solver as well. And so on the heuristic side, we can encode domain-specific knowledge about this memory allocation problem, and then basically work with the solver to guide this search and solve this NP-complete problem. Every once in a while, the heuristic will get stuck. So in this case, it has to backtrack and try something else. And so this approach didn't use any machine learning yet. And this is something that we actually shipped in production. So this is in Pixel 6 and also in the TPU-v4 compiler. And one thing I want to emphasize is that this is something that is really for the long tail of inputs. A lot of the inputs to the compiler can be and will be handled by a heuristic. Heuristics are usually much, much faster. So conventional techniques can cover a fairly large chunk of the space. But then for the very long tail of inputs that solvers have difficulties with and run for a long time, that's something where we can basically have the heuristic and the solver work together in order to solve these. But even with this approach, there are still inputs in that space that it couldn't solve. So we're asking ourselves, is there something we can do here to solve even more of the possible inputs? And this is where we tried, as a research project, to apply ML for systems. And I think this is a pattern that actually applies in other spaces as well. So the problem that we're trying to solve here is that we have the heuristic and the solver work together. They got to a point where they are stuck. They know that the problem is now unsolvable, and they have to backtrack. And so the question is, how far should they backtrack? And so the idea here is, this is something we can use machine learning for. We could develop a backtracking heuristic, but it would be very complex because it would need to take lots of different parameters into account to make that decision. So instead of doing that, can we just learn that backtracking policy? And so the way we do this is with an approach using imitation learning, where we run the allocator a number of times. When it backtracks, we have the ILP solver figure out in the background how far should it have backtracked. So that way, we now have a data set of examples where we know for each individual case what would the ideal number of backtracks have been. And then we can train a model against this. It's a fairly cheap random forest model. And then once you have this model, you just plug this into the allocator as a learned heuristic. And so this is an example of this discovery pattern, where offline, we basically use this process to learn a new policy that then can be directly plugged into the memory allocator. And this is something I think that applies in a wide range of different areas as well, where there is a component where we could write a complex heuristic, but instead we can just learn a policy offline and then plug in that learned policy. So these are just two examples. There is a range of different problems in this space that have a similar structure. And so that brings me to the end of the talk. And I think there are a couple of takeaways I would like to leave you with. So machine learning for systems, I would argue, is a growing but still an emerging research area. But it is also an area that has a significant amount of promise. And I think this makes it exciting because it is still early enough that there are lots of problems that are simply not solved. And there is a lot of really interesting and impactful work still to be done in this area. I also want to argue that because the area is still in its early stages, it hasn't really coalesced yet around a shared methodology and terminology. And I think as the field is evolving, it's going to be important to build more of these common data sets, common benchmarks, best practices, and so on, and basically have, for example, a clearly defined set of baselines, clear, well-defined set of things to try, and so on. And finally, when looking at ML for systems, I think it's very important to look at what is the thing that machine learning allows us to actually learn that we couldn't do without machine learning. And how much can we focus our machine learning approach on just this one sub-aspect of the problem? Because the more we can focus the machine learning technique, the more likely it is that it is going to have the maximum impact and is maximally practical. And so with that, I'd like to wrap up and looking forward to questions and discussion.
Cool. Thanks so much for that great overview. It was really interesting to hear you talk. And of course, thanks so much for coming on. I'll go ahead and stop your screen. Oh, thank you so much. You stopped the screen share already. So we can go ahead and have the conversation. They see our nice faces this way. So I think one thing, I'll just go ahead and with the questions. Of course, if you're on YouTube or the Discord, feel free to ask questions. Our chat is over there, so we'll be monitoring the chat and looking for those questions. I think from a high level, something I was kind of curious about early on. So you mentioned kind of at the beginning, one of the things that you're interested in is how can you achieve something more cheaply? And I was wondering kind of how do you think of what those relevant metrics are? So in my mind, there's like, from a machine learning perspective, there's the cost of collecting data, doing the training, all of those, but then there's kind of the costs of let's say actually running the model or running the model compared to some other heuristics. So how do you kind of balance the cost of we need to do this to kind of train our model compared to like, this is how much it costs to run our model versus if we run our model here, maybe it's not as optimal as, I don't know, doing something else. How can you like kind of, give us some perspective on how you think about cost there?
So I think it's important to start with the cheapest possible option in any case. And in a lot of cases, that's actually a lookup table. So I think one of the challenges of machine learning is that because you're oftentimes going from a non-data-driven baseline to a data-driven approach, that it becomes this question, what is the simplest possible thing you can do? And so one very easy thing to try is, what happens if I take my training set? I just put it into a lookup table, plug that in. Now I have a data-driven policy that is about the cheapest data-driven policy I can possibly have, and see how well that does. And sometimes actually lookup tables do surprisingly well, because a lot of benefit comes from just going from not data-driven to data-driven at all. But sometimes it also turns out that that's not tractable. For example, you have something that requires just more logic to aggregate the training data, or the training set is just too big to put into a table, and so on. And then you can climb up the ladder. Basically, okay, lookup table did not work. Let's go to a decision tree or random forest. Okay, that doesn't work. Maybe a simple neural network. And if that doesn't work, maybe a transformer. And basically just climbing up the stack until you get to a point where it works well enough, and has the minimum cost.
Great. One other question that I was curious about. So you kind of described with things like this lookup table, or you talked about how you would kind of run a model and kind of watch it run and then send something to the machine learning model. How often do you see, like in machine learning, we care a lot about things like generalization from like new workloads or unseen things. How are you seeing things like that where like you can learn something from the variable names in one program and it'll transfer over, or are you kind of at the stage where you need to run every new program through the whole process?
So the paper I mentioned in the middle, where we're trying to generalize across programs, is taking a little bit of a look at that. And I would say you can learn something, but it is very difficult to get very accurate predictions. So I think that we saw some signal that you can do better than random, and that there are some things that you can pick up. But I think sometimes generalization can be hard. And I think a big piece of this is that systems have a fair amount of unpredictability. And so if you have two systems that behave in a very similar way because they have a lot in common, then you're more likely to be able to generalize from one to the other. But you could have two systems that just are completely different. And then generalization is difficult, even if you have, say, shared components within the code.
Got it.
Yeah.
Cool. Yeah, because it would just be really cool if like, you picked up on like something like, a particular pattern of variable names meant something. But go ahead, Ben.
Yeah, so I have just kind of a broad high level question here, which is that ML4Sys obviously can provide these big performance boosts, but it does so at the expense of additional complexity in both the engineering, especially also the behavior of these systems, which can get very complicated since you no longer have the clarity that you once did when it was all deterministic and algorithmic. And so, it seems very clear to me that at Google scale, like this is worthwhile, right? That's a good trade-off that you make at Google scale. But how would you reason about this for smaller applications and smaller workloads that aren't quite, at the like $1 billion of compute per year level?
So I would look at it from a slightly different perspective. I think the question is, what is it that machine learning buys you? And I think the example I gave with the allocator is a really interesting one, because there are a lot of input problems in this case that you can solve with traditional techniques, and you can improve traditional techniques and solve even more of them. But there is this really long tail that is very, very difficult. And if you need to support that long tail, then yes, you might end up paying more in terms of performance. But in return, you kind of get a step function difference in I can now support this input that I previously couldn't. And so in my mind, the best applications of machine learning in systems are the ones that give you this kind of step function improvement. And I think that is relatively independent of scale. But in all other scenarios where it's basically you're looking at a trade-off space between you're incurring some costs and in return of that, for that cost you get some benefit, then it becomes a kind of classic cost-benefit analysis. And I think you touched on a couple of really important areas. The cost is not just in compute resources for running a model; it is in complexity, interpretability, basically the kind of practical like complexity arguments around systems.
We have a bunch of great questions from the class, so we'll go ahead and start asking some of those. And of course, if you're on YouTube, you can also ask questions. So I think one really great question comes from someone in the class. What systems problems do you feel ML can make a significant impact on that still kind of remain underexplored?
That's a very good question. I would actually say it's probably any important system problem probably has space right now to do something. Right. And this is to my point that it's actually still fairly early in this area. I don't think there's any systems area where it's basically, yep, this is solved now. Actually, so what I would recommend is actually to look for systems problems where there is a lot of headroom. So and that is very specific to the individual setup. So if whenever you can take a problem and you can put a bound on the headroom, it allows you to say, okay, there's at least another, just making something up, there's at least another 50% of efficiency here. Those are usually a good place to apply machine learning because you know that there's actually still a lot of gains to be had. Whereas if you have an area and you basically can calculate, okay, this is the optimal efficiency of the system, and the system is at 99%, that's probably not the best place because it would probably be a lot of complexity with little payoff. There's actually, I think, a related topic, which is how do you actually get to this headroom? And so I think one adjacent research area to machine learning for systems is analyzing systems and actually finding out what is the ideal you could do in this case. And those problems themselves can be very hard. So for example, in the memory allocation case that I showed with the machine learning accelerators, to find the optimal solution, you need to solve this NP-hard problem. That in itself might actually be a really hard problem to solve. Right. And so there's kind of this meta problem as well of how do you find the right problem, and ML for systems might even be able to help with that.
Right. Yeah, I think in the type of work that I do a lot, it's a lot of, writing CUDA kernels and looking at, what's the arithmetic intensity and how close are you to the memory bandwidth or like kind of flop utilization numbers that are theoretically possible. But yeah, certainly, looking at those heuristics, I think is good. There's another great question is, what are some examples of previously unknown system properties that cannot be handled by an ML solution?
So I think it's difficult to predict what can't be solved by ML. But I would say actually anything where you need to connect user intent to the behavior of the system is hard. So the example I gave with AI for code, I think what makes this interesting is that if you had something like a lower level system, without being able to reason about the code, it just didn't have information to go by to make its decisions. And so there was this fundamental limitation in a way of the system can do as well as it can with the assumption, and the assumption is basically the workload could be anything, and I don't know what it is doing. And if you can now reason about the workload using ML, then that opens a whole door of opportunities doing something you couldn't do before.
Cool. There's another question from the students. Can you share any metrics indicating to what extent these methods improve the user experience? For example, for the Pixel phones, can you share anything about, I don't know, they made pictures faster or something?
Yeah, the paper has numbers for different kinds of models. How much faster is it than the solver? And it also has numbers for the heuristic. So it shows, for example, that if you can run the heuristic, it's this much faster. But if you had to run it with the solver, it would take this long, and then with the allocator, it takes this long. I don't know the numbers off the top of my head, so I'll defer to the paper. We also show, we look at a fairly large number of models to understand this tail end of the workload, and we show that there are a number of models at the tail end that we can solve with telemalloc that the heuristic or solver both didn't solve before.
Gotcha. I'm actually curious about that situation. So is it the kind of case where the heuristic was already kind of very good, but the ML model is a cheaper way to get at that and it's faster? Or is it the other way where the heuristic is very fast, but the ML model maybe is a bit more expensive than the heuristic, but kind of gives you something that is closer to the solver?
It's the latter. So the heuristic is very fast, but sometimes it won't be able to solve the problem. And okay. It will always run the heuristic first. So telemalloc only gets run if the heuristic fails. So telemalloc was very specifically looking at the cases where the heuristic couldn't handle.
I see. Okay, and that's a case where you can tell that there's it's not say like there's a 5% difference in performance at the end of the day, but there's something, you know, drastically kind of catastrophically going wrong if you don't find a solution.
Yeah.
Okay, cool.
So one question I want to ask is that most of the techniques that you've described in the taxonomy are sort of on the deep side of, you know, deep learning, right? Deep learning based techniques. And I guess my question is, how do you weigh this in the overall ML for systems landscape versus the, you know, the learned data structures, the kind of like the put a linear regression everywhere philosophy of it that has also been explored, you know, at a kind of the highest level of if you're actually engineering a learned system from scratch?
I would say they're in the same space. I think learned data structures are an example of data-driven methods, and I think it's actually a particularly good area because this space has actually been a little bit more explored in terms of what is the trade-off between different types of representations and what the costs are that they incur. And so I think it's a very good example of this, asking how much complexity and how much cost do we need to get the accuracy that is sufficient for the use case. And then the other thing that is a connection to some of what I talked about with C++ memory allocation is that these learned data structures are typically just one piece of the broader system. And so you use machine learning just for this one piece, and then the rest of the system gets designed on top of that. So it's a good example, I think, of the approach.
Speaking of kind of those questions about cost and also model selection and things, we have a question from the class. In telemalloc and kind of the other related works in your experience, how much bandwidth or compute is it worthwhile to kind of allocate to the machine learning models?
Well, that's very specific, and I think a big question of that is offline versus online. So if you're training something offline, for example, and then you plan to deploy it and it won't get retrained very often, you can do a lot more than if you have something that needs to run online. And I think the guiding factor there is the payoff. If you know that you can spend X resources and get 100X resources back, then it's worthwhile. But if you basically break even because the model is too expensive, then it's probably not worth it. So it's very problem specific. And I think one aspect here is that a lot of this work is really very, very specific to the system side. And so to me, that's one of the things that make this area particularly exciting, because it's one of these things where it's not just it's not just the machine learning or just the systems. Work really needs to dive deeply into both and figure out how do you trade off the different costs or things like accuracy against one another.
Gotcha. One more question from the class. How does anomaly detection kind of apply in autoencoders?
There is some autoencoders is one way to do anomaly detection. There's a couple of papers out there. It's basically you use the autoencoder to learn the normal behavior, and then it tells you basically when you start to diverge.
Gotcha. So kind of moving on to some more questions that I think we were just curious about. So one, I think when, if you kind of recall in popular culture, when we had like AI chess bots beating the best, chess people, and AI Go beating people in Go for the first time, the experts said that they could kind of learn from the AI techniques and kind of take new strategies and approaches. Have you seen that happen at all, where you watch the ML system do something, then you learn something that you can then go take back to kind of a traditional systems approach?
Yeah, so that happens, I think, pretty commonly in this area. I think one example is the C++ memory allocation work that I talked about was a research project. But we learned some things from that project that we then built into TCMalloc. And those things are not machine learning based. They're about the way that we manage pages in TCMalloc. But those are actually deployed, and they're in open source TCMalloc and so on. There's another paper about it that I didn't talk about here. But that's an example of we did this project and then we learned something and we applied it.
Can you give some like flavor about what you learned, or if there's a one-line takeaway from the ML, what would that be?
Basically, that this pattern that I showed with the large pages versus small pages, basically there are different ways of addressing that. And what we did in this work was basically looking at a time series of that and then making decisions based on a time series rather than at a time.
Gotcha. And then, there's advantages from kind of distilling that, because then you could maybe write it in a quick heuristic that you can always run, as opposed to running this big bundle to discover something that you can distill out.
Exactly. So it's basically collecting a time series and looking at the last couple of minutes and then using that to make better decisions.
Gotcha.
So one question I want to ask as well is, there's always trade-offs in systems between kind of local optimization of here's some little problem, let's, go like make that work better, versus kind of a larger co-optimization of let's redesign the system with this new stuff in mind. And so, do you foresee most of the gains occurring at this kind of local optimization level, or do you think that we really need to rethink the systems from scratch, the hardware, the whole kind of architecture to better make use of these new techniques?
I would say it's probably little bit of both. So in some cases, there is a lot to be done around the local optimum. So basically, by identifying there is a technique, there's a heuristic here. Heuristic is important. There's this much headroom. Let's replace the heuristic. But then there's also examples of could you redesign the entire system? And I think sometimes one leads to the other. So with the C++ memory allocation example, we started off with these lifetime predictions, but then the question becomes, if you actually have lifetimes available, how do you build a new memory allocator around it? And this becomes a very different kind of memory allocator, because traditionally memory allocators are based around size classes, because that's the information the allocator has. But if you know the lifetimes, you can basically design the entire allocator around lifetimes instead. And so it ends up being quite a different design. And I think that is something that is fairly common, where people start playing with machine learning in a systems context, maybe make some local optimizations using it, but then that leads to, oh wait, now that we have this new prediction from the model, how do we actually redesign the rest of the system around this prediction?
Well, very interesting. Maybe a more general question, or maybe you can answer specifically for different workloads. So when you talk about things like the C++ memory allocator, how often is it the case that you actually need to kind of run the program and watch it evolve over time? Or how often can you do something akin to more static analysis where you just run it? Obviously, there's the halting problem. So at some point, there's always going to be some adversarial case where you have to run it. But how often is it which bucket are you kind of looking at there?
So the good thing about a lot of these areas, not just memory allocation, but a lot of the kind of traditional systems areas, is that the methodology is oftentimes pretty well established. There's benchmarks, there is kind of metrics describing this is how I'm going to measure it, and so on. And in a lot of cases, the ML approach plugs pretty much directly into the established ways of evaluating that work. Yeah.
Gotcha. Let's see, I think, Ben, you have a question.
Yeah, I've got one more. Yeah, so I guess going back to what you said earlier about kind of the step changes for, different kinds of tail end inputs as opposed to more kind of broad, I guess, in general, I'm sure there's going to be different problem spaces, but for different kinds of problems, how big is that long tail?
Yeah, that depends a lot on the scenario. We did a bit of a study in the storage space. It was a paper we did in MLSys a couple of years ago, where we basically looked at different models to predict storage behavior. And we basically found a lookup table covers most of the space. KNN then covers most of the rest. And then with a transformer, you can cover even more. But it's basically almost like a power law thing where you basically make your model more complex and you basically cover exponentially more things over time. I would say that there's probably no one-size-fits-all answer just because it's very specific to the problem. I think anything related to code, for example, has a lot of just a very wide range of different languages and patterns and so on.
Cool. As we kind of get, I guess, near closer to the end of the hour, I kind of wanted to turn the conversation to more, weirder, forward-looking things. I wonder what your thoughts on, let's say, 5-10 years from now, how integrated is machine learning going to be, kind of like the whole system stack? Are we going to see ML models in the Linux kernel and everywhere? Are we going to see it kind of like, and work throughout? How do you kind of envision that evolving in the next 5 to 10 years?
A very good question. I think we're gonna see more and more of this work. I think we'll see more and more sharing between different approaches, which will help accelerate it. I think one of the big problems right now is that if you want to get started in this area, it's often very hard because you need to get a lot of infrastructure off the ground, and oftentimes you run into the same kind of roadblocks over and over again. So, for example, how do I make my model cheap enough to run it in this particular context? Or how would I get my model into the Linux kernel? But once those hooks exist, it becomes a lot easier to then build on top of them. And so what I suspect, and this is just my personal hypothesis, what I suspect is that as more and more of these general solutions become available, it would also accelerate the use because it lowers the barrier to entry. And I think that makes it a very exciting time for the community to start building on these general things, because I think that's what will enable a lot more work.
The one thing I think we're also starting to see is we're starting to see ML products, large language models and such, be integrated kind of everywhere across the product stack. Like I think my storage services are saying there's an AI solution for that now and stuff like that. Kind of something that we've joked about before is like one day you're going to have your toaster have a full language model that can talk to. Why do you need a toaster to talk to? As you kind of like see that happen, that integration of like kind of these other machine learning models get integrated kind of everywhere through the product stack, how do you see that changing this conversation about ML for systems and ML for systems for ML? It's kind of all circular like this.
That's a very good question. I think one of the things in the ML for systems space is that models are evolving and systems are evolving. And so whenever there is a new model or some new capability, the interesting question is, how does that help with systems? And I think it may end up being very case by case once again, because some systems have very little work yet on applying machine learning within them. And so there is still a lot of headroom with much simpler models, but there may very well be areas where simpler models just won't work, and where one of the more modern models has some capability that allows you to solve just problems that you previously couldn't have even considered solving. And so I don't think I have a general answer to that question. But I do think we're going to see some really interesting applications of some of these more modern models in the system space as well.
Cool.
One random question. Do you worry at all about the security implications of these learned systems potentially leaking kind of workload data or program data in some unintended way, by virtue of where they allocate memory or similar things?
So I would broaden this question a little bit. I think there are a number of research problems around ML for systems that are beyond the just learning and efficiency, for example, questions, but they are about what you mentioned, like safety, security, interpretability, predictability, and so on. And so I think there is this is an area that the community is starting to talk about. We had 2 workshops actually about this topic at MLSys in the last 2 years, where we basically just tried to bring people together from industry and academia to talk about these problems, and it was very interesting because there were just lots of different perspectives of there's these additional challenges that are kind of orthogonal to the how to apply the learning, but yeah, how do we make it safe? How do we make sure we understand what the model is doing and that it doesn't do the kind of things that you were describing? And I think those in themselves, they are research areas that exist in other areas, and they apply to ML for systems the same. But I think they haven't seen that much attention yet. And this is another space where I think a lot of cool research could be done.
Cool. All right, so we're getting to the end. I always like to end with kind of a open-end question. Just sort of, what are you excited about? What are you excited about doing next? And what's coming up on your plate? What can we expect to see from you coming up?
So I'm currently very excited about AI for code in general, and the implications that it has. I'll leave it at that.
Okay, cool. I'm also excited. I have my Copilot on when I'm writing LaTeX as well. So sometimes it suggests nice sentences and things. Cool. So I think with that we're gonna call it for today. We'll go ahead and say goodbye to YouTube. If you're watching on YouTube, you can find our schedule and everything at mlsys.stanford.edu. If you go to that website, you can find a bunch of stuff about our schedule. We have a mailing list where we only email you something like once a week. So there's not a lot of spam, but there's a couple thousand people on that who hopefully tune in every week. If you what else do people say? If you like the video, like and subscribe, hit that notification icon, that bell icon. But with that, we'll go ahead and wave goodbye to YouTube, and of course we'll thank Martin. So bye YouTube, and thanks so much, Martin, for coming on.
Thanks for having me.